Welcome back, everyone. I'm Dr. Rhett Smith for ProtonGuru.com, covering Lesson 6.9 in our discussion of carbonyl chemistry. And today we're going to look at some facile nucleophilic acyl substitution, abbreviated SnAC, on acyl chlorides and acid anhydrides. This is what I categorize in my text, the Organic Chemistry 2 Primer, as a type B reaction. Just to remind you how this type B reaction takes place, you have a nucleophile that attacks the carbonyl carbon, with nucleophilic addition leading to initially a negatively charged oxygen species like this. And what this reaction requires for the second step is pushing this Y group off. Now, if this Y group is already a good leaving group, meaning that it can form a relatively stable anion by itself, then this happens spontaneously without the need to add any other reagents. And this happens to be the case if the Y is a chlorine, which is the case if we have an alkyl chloride, or if that Y, let's say Y- is chloride, or in an anhydride. Remember, you have that second carbonyl, so you'd have a resonance stabilized anion, and that's why you have a stable leaving group Y- for those two cases. So the acyl chlorides and the acid anhydrides undergo nucleophilic acyl substitution very, very readily with even very weak nucleophiles. Let's look first at the acid chloride and consider three different pretty common nucleophiles that we can use for this. The first nucleophile we'll consider is this carboxylate. Now remember, the first step is that you're going to push the minus charge up onto the oxygen and attach the nucleophile, and the second step will be pushing this leaving group out to reestablish the carbonyl CO double bond. So in the end, what we will get is nothing really happening to this piece, but we have the nucleophile piece, this piece that was the carboxylate, now attached in place, or substituting for, that Y group. In the acid chloride, that leaving group, if you're balancing everything, is Cl-. You have an Na+ that's sort of a spectator anion. So at the end, you could isolate a sodium chloride salt and now an acid anhydride from the acid chloride starting material. Now, if we use an alcohol or water as the nucleophile, where we have ROH, or in the case of water, which would do very much the same reaction, HOH, we would have nucleophilic attack like this. And remember, when water or an alcohol acts as a nucleophile, we also have a deprotonation step, either at the same time you have the nucleophile attack or in a subsequent step. So the net result would be the replacement of the Cl with the nucleophilic piece that stays on the molecule, this OR group. So that we would get the O with its R prime group, our double prime group, that's the piece from the starting material here, right? And then this is the piece that eventually replaces the chloride. So we have OR. If we started with water where this was an OH, right, we'd have an H here. But here, in the case I show with an alcohol, we've made an ester as our product, and the Cl- is floating around. We have the proton that came from the alcohol floating around, so you have HCl that could come out as a gas, or you could neutralize that in your solution with a base and isolate your ester that way. If you use an amine instead, well, you replace the O with an N, and there has to be a hydrogen on the nitrogen. So this nitrogen that I draw here has an R prime group, an R1 group, right, kind of a strange representation, and an H group. So it looks like this, but it has the lone pair. Just like when you use alcohol or water as a nucleophile, the nitrogen is pretty electronegative. It doesn't have the propensity to make a positively charged nitrogen if it doesn't have to. So it tends to lose that proton as you're attacking. And this R prime or R1 group can be alkyl, aryl, or another hydrogen. Now the net result, right, the first step is just doing the nucleophilic addition. But then you're going to push that negative charge back down and release the chlorine. So the chlorine will be off. You've got the proton that you took off of the nitrogen. And now you have this piece from the carbonyl, just like we had it up here and here. And the nucleophile, in the first case was the carboxylate, in the second case was the OR. Here it's the N with both of its R groups, right? R prime and R1 we called them. So you make an amide from the acid chloride very simply, very easily, by adding an amine to the acid chloride. Very similar with the anhydride, because the reactivity of these carbonyls really depends on whether this is a good leaving group or not, or whether we might need some other reagent to make it a good leaving group. Anhydride, like the chloride, has this group that's already a good leaving group. So if we say use water as the attacking group, we again have to think about doing the attack with loss of proton. The net result then would be that you replace this whole big leaving group. Let's draw that out here. That's going to be common to all these reactions. With its replacing that with the OH group and having a proton, which could go with this to make a carboxylic acid. So this half of the molecule, let's draw that in here. We have the second half of the molecule with now an OH group on it. So really we've gotten two equivalents of the carboxylic acid, if you have the correct pH for the carboxylic acids to keep their protons in these two cases. If instead you use an alcohol, of course you would have addition of the OR1 group, right, that part of the alcohol, just like we went through with the acid chlorides on the previous page, plus the leaving group with that proton that came off of the ROH, and we'd have the carboxylic acid. So you get an ester and you get a carboxylic acid. And if we use an amine, very similarly to what we saw with the acid chloride, we would again have this leaving group that is from the anhydride right here, and we would have the other half where that leaving group site that was attached right here is replaced by the attacking group, which is the N with its R prime and its R1 groups, and the H that came off of the nitrogen. So you've made an amide and a carboxylic acid. One question that comes up with anhydrides is that there are actually two carbonyl sites that you can attack with a nucleophile. And the question would be, what if those two sites were different? If I had, for example, a relatively simple case where I have a methyl group on one side and an ethyl group on the other. Well, you'd have a mixture where you have attack at one or the other sites. And there's not a huge difference in these rates unless the steric bulk at one side becomes much larger than the other, let's say. Then you would shut down that pathway relative to the other. Generally, in an introductory course, you tend to focus on symmetric cases. Let's say we had to do a more challenging problem where we had an ethyl group on one side and a propyl group on the other side. And let's say we were using methanol, MEOH, as our nucleophile. Well, the attack of the alcohol as a nucleophile on the left-hand carbon would lead to an ester forming like this. That would lead to the other half breaking off as the carboxylic acid. Because the sterics are so similar on the left-hand carbon and the right-hand carbon here, we would expect the methanol could attack this carbon, which would lead to the production of this ester with the methyl going here. There's your ethyl group. And then the other half that wasn't attacked, being the leaving group, would leave us the carboxylate that got protonated, let's say. So we'd expect actually a mixture of all four of these compounds. Right? But if your anhydride is symmetric, you can attack either side with the same rate and get products like we show in boxes A, B, and C.